The intensity, L of x, of light x feet beneath the surface of the ocean satisfies the differential equation dl dx equal to minus kl. From experience, a diver knows that diving to 17 feet in a sea cuts the intensity in half. He cannot work without artificial light when the intensity falls below 1/10 of the surface value. About how deep can he expect to work without artificial light? We know that the function that describes the intensity of light at x feet beneath the surface of the ocean satisfies the differential equation dl dx equal to the opposite of k times L. If we were to multiply both sides by dx and divide both sides by L, we would wind up with dl over L equal to minus k dx. Integrating both sides, we would have dl over L equal to integral minus k dx, which would give us the natural log of the absolute value of L plus c equal to minus kx plus c. Since both of these are arbitrary constants, we could combine both constants onto one side, and we would wind up with the natural log of the absolute value of L equal to minus kx plus c. If we convert this into its exponential form, we would have e raised to the minus kx plus c equal to the absolute value of L. Since L is an intensity of light, it'll be positive, so we don't need the absolute values. We also know that when we multiply with like bases, we would add the exponents, and our exponent here is a sum. So we could write this as e to the minus kx times e to the c. But e to the c, again, is just a constant. So we could write this then as L equals c times e raised to the minus kx. Using the relationship that we're given, that at 17 feet below the surface, the intensity of the light is cut in half, we can write c times e raised to the minus 17k equal to 1/2 c e to the 0. On the left-hand side, we have the expression of the intensity of light when x is 17, and on the other side, we have expressed the intensity of light as half of that when x is 0. We could divide both sides by c, and we would wind up with e raised to the minus 17k equals 1/2, as e to the 0 is 1. If we were to natural log both sides, we would have the natural log of e raised to the minus 17k equal to the natural log of 1/2. But the natural log of e raised to any power is just that power, so we have minus 17k equal to the natural log of 1/2. Dividing both sides by negative 17, we wind up with k equal to the opposite of the natural log of 1/2 over 17, and from our log properties, we know that we can express this as the natural log of 2 over 17. So we have identified a value for k, but the question remains, what is x when L of x is 1/10 of the initial intensity of light? Recall that L is equal to c times e raised to the minus kx. So in this case, L of x would be equal to 1/10 of L of 0. Now, substituting, we have c times e raised to the minus kx equal to 1/10 c times e raised to the minus k times 0. Again, dividing both sides by c, we would have e raised to the minus kx equal to 1/10. Taking a natural log on both sides, we would have minus kx is equal to the natural log of 1/10. Dividing both sides by minus k again, we have x is equal to the natural log of 10 over k. But we know k k is the natural log of 2 over 17. So we have the natural log of 10 over the natural log of 2 over 17, which we could express as 17 times the natural log of 10 divided by the natural log of 2. Rounding to one decimal place, the result is 56.5.